Thank you so much. Yeah, thanks for the kind introduction, and I'm super happy to be at LUOV, right? And today I'm going to talk about a specific type of attacks we discovered a couple of years ago, 2 or 3 years ago, and that we have been able to apply in a number of schemes, and specifically on post-quantum schemes. That's where pretty much everybody's headed, so are we. And so without further ado, so we all know the announcement, right, that came out a couple of months ago. After 6 years of competition, NIST finally declared the U.S. National Institute of Standards and Technology the winners of the post-quantum competition for key exchange mechanisms and signatures. And specifically, Crystals-Dilithium came out as the signatures winner with Falcon and Sphinx Plus as backup, and Kyber, right? Crystals Kyber for Chem. Because this talk is mostly about signatures, that's why those are highlighted here. And then, but we have lots of other interesting schemes, right, that are still interesting, and maybe some of them might still get standardized in over time. We'll see. I mean, these are the round 3 finalists, right, that were last in the competition before the winner was announced. And I'm also a practitioner, so I like to see how these fit into actual applications, right? So this is a plot that shows you in log scale, so both axes are in logs, of the public key size and the signature size in bytes, right? Log of bytes of the signature schemes that made it to round 2. And you see that hash-based schemes are mostly, they have massive signature size. Their public key sizes are a little bit smaller than others. Versus on the opposite extreme, we have the multivariate-based schemes that have much larger public keys, but their signature sizes are small. And somewhere in the middle, we have the lattice. And remember, this is a log-log scale, so it's more like a curve, really. So from a practical perspective, if you add, let's say, the public key size and the signature size, clearly the lattice-based ones are much more efficient, or maybe usable in practical applications where size matters. And those two highlighted in the middle, the light green ones close to the optimal point, that's Falcon, and the one that is slightly above, right, the slightly more bluish colors there, that's Dilithium, right? And if you want to look at Sphinx, that's the light yellow on the left. And you see, compared to ECDSA, we have much, much bigger size on everything. I mean, this is no surprise here, right? Public key is costly. Now, we can, of course, these public key schemes have been designed to resist quantum attacks, and they come with all kinds of reductions, right? And the problem is these schemes are still vulnerable to side channel, right? We can, use our standard physical channels, such as power time, EM emanation, and so on, as well as active attacks with fault injection, either old style, glitch the voltage source, the clock, or more new age, let's say with Rowhammer and software level attacks. We can attack them, and my slides tend to be a little bit boring, so I prepared you a meme instead, right? My first and probably last meme, so. And if you want to, do a physical attack, you need some kind of setup, right? And this is more like the traditional old-style physical, more chess-ish. Let's say the chess community, right, has a lot of these papers where it started very naively, simply with an oscilloscope and, some power source, a few probes that you buy for a few $1,000s. And then more recently, people have moved on to more sophisticated setups. Automated probing station, something that's riskier, would sell you for over 100K. And now we're moving into, these super sophisticated machines, either like this is a FEMO station, costs over $1 million, but you can very precisely, using laser, read off bits off of a chip. And similarly, you can have fibs and, all kinds of more sophisticated devices appearing. But from my own perspective, I'm more interested in software-only attacks. And these are more recently emerging attacks. Yes, we have known about cache attacks for a long while now, over 20 years. but the so-called microarchitectural attacks have proven successful. These are stemming mostly from optimizations or bugs in microarchitecture design. Intel, for over 30 years, they have optimized their CPUs to forward data before it's needed, speculatively executing across branches and so on. So all of these optimizations have opened the doors to a number of attacks. We have known Meltdown, right? And Spectra. Meltdown is mostly fixed now, but Spectra is still around. These are so-called speculative execution attacks, right? And that use the transient domain, and you can leak information from the transient domain. That's not meant to be leaked across processes. And in the last 2 years, 2.5 years, Mds attacks have came out. These are more thread level, hyper-threading related, right? So if you're on the same core, turns out Intel and a bunch of other companies are using internal buffers to do optimizations. There's like a line fill buffer and a bunch of other buffers that are shared between threads, you know, between hyper-threads, and you can leak information across. And these were shown in, you know, some famous papers like Riddle, Layout, Fallout, Zombie Load, etc. And LVI is an interesting case where you could actually inject data to other processes using it in the reverse form in the transient domain, you know, from one hyperthread to the next. And as far as active attacks are concerned, Rowhammer, Plunderwald, and more recently, voltage and frequency scaling attacks have become, you know, more prominent in the last few years. And the main advantage of these attacks is you don't need any of this sophisticated equipment, right? These are cheap. All you need is a laptop and some code, right? So no need for expensive equipment. As long as you have software access, you need still software co-location. And it's a much lighter form of co-location. Here you need the physical device to be present, right? You need to hook up probes into it or put it under a laser station, right? In a harness. And here you don't need that, but you still need to be able to run code on this remote device, right? Somehow. Either by renting a cloud server that is shared, right? Amazon has these machines that are shared among many guests, right? Guest operating systems. You spin an instance, immediately get co-location out of the box. Or it could be, you know, maybe your code, your attack code is embedded in a browser in JavaScript or WebAssembly. And then, you know, whoever loads the browser, right, visits that site, right, that loads automatically in the browser, and you get access to their information. So 2 ways that I know at least of getting co-location. All right, so back to post-quantum schemes. So side channel attacks work differently on post-quantum, right? We have pretty much the same channels as before, whether it's physical channels or microarchitectural channels. And but the post-quantum schemes have typically simpler structures compared to RSA, where you're, you know, taking 1,000-bit numbers or 2,000-bit number, raising it to a 2,000-bit number, or elliptic curves. You have typically matrix vector operations simpler, but you have nearly linear operations, right? Much simpler structures. But on the downside, everything is huge. It's massive. You have a, let's say, 256-bit ECDSA key, right, for signing, compared to kilobytes of key material in a typical post-quantum scheme. So if you're doing an attack, it means you have to do a lot more work getting these bits off. And given that you have less algebra to play with, right, it will be more of an incremental process getting there. So that's how I see it, at least in my experience. So here's an early attack on Bliss that I really, really like. This was, Bliss is an somewhat older post-quantum scheme, one of the earlier ones, where Dukas et al. Proposed a scheme, a lattice-based signature scheme based on bimodal distributions. You can ignore the bimodal stuff for now. And the attack that followed that was flush Gaussian reload, a cache attack, a very nice cache attack, targeting Bliss's samplers, actually, and they're using the standard flush and reload, which is a very efficient cache attack, right, that targets L1 caches. And after observing only 3,500 signatures, they're able to recover the Bliss key, the entire Bliss key. And the target is the discrete Gaussian sampler. So this is just the algorithm shown, right? So you see the highlighted portions. The step 1 samples 2 nonces, Y1 and Y2. Bimodal, that's why they do 2 samples. And from a distribution, truncated distribution, Gaussian distribution with some standard deviation. And Y1 and Y2 are absolutely essential. They need to hide the data that is contained, otherwise leaking from S1 and S2 in the signature steps in 5 and 6. And to sample the Y1 and Y2 in step 2, Bliss uses a CDT samplers that use a large lookup table. As soon as you say lookup table that is data dependent, enters side channel attacks, right? So cache attacks. And this is a quite beautiful flush and reload attack where they use the algorithm, the structure of the algorithm to recover the most significant bits of Y progressively. So you're doing a bisection kind of an attack, just based on the axes, right? And using that later on, they mount an, with the partial knowledge of the Y values. If you get the higher bits of Y, that's wonderful leakage, and you can use that from that. And in their case, they just need only 3,500 signatures. So there's a little bit of algebraic manipulation going on here, but it's not complicated. Okay. So anti-fault attacks. So the specific attack I'm going to show you today, signature correction attack, is based on faults. And there's a bunch of fault attacks proposed in the community on Bliss and other kinds of signatures as well, right? So I'm focusing only on post-quantum signatures that have been targeted for faults. And there is one line of work that followed the old differential fault analysis approach, where you have a signed message and then the same message being, let's say, signed again, right? And you look at the differential, right? When you inject the fault in the second signature, you look at the differential, and that reveals some information. And yes, this was proposed by Brudering, for example, against deterministic lattice signatures, deterministic being the keyword there. And, and actually some of the competitors proposed randomized versions after that. So this was still impactful research. But currently we don't have any that doesn't support randomized signatures. And these types of standard differential fault attacks, at least the ones that I'm aware of, don't work on randomized signatures. So anti-signature correction attack. So this is an attack that we proposed in 2020, discovered in 2019. And it's an active software-only side channel attack. And it applies to randomized and deterministic schemes. It's agnostic to that. It requires co-location with the victim because of the way we inject the faults. If you have another fault injection mechanism, that's fine. You can use that. It doesn't, co-location just means you have some kind of access that allows you to inject faults. And it's algorithm dependent. So for every new algorithm, you have to look and see if it still applies and works or not. That's sort of a downside of the attack. And we need to be able to inject faults and collect the faulty signatures based on, as always, right? So there are 3 phases to the attack. There's a templating phase, an online phase, and then a post-processing phase, 3 phases. And the templating phase, the particular attack that I'm going to present uses Rowhammers, right? It's a software-only attack to inject faults. And we start out by profiling lots and lots of memory pages. So the victim doesn't have to be around or executing or even present in the system at the time. But we should know that they're gonna, be instantiating a process that's gonna perform signature operations on the same system. We profile memory pages, and our goal is to find locations in the DRAM that are flippable. On average, about 4 to 5%, right? Depends on of course, on the physics, on the device, right? Different manufacturers have different levels of reliability, but you get about, let's say 1 to 4% flippable locations across the board. And these are somewhat random. There are some biases, obviously. They're not, uniformly distributed, but we can assume they are. So there are very few flippable locations, just out of the box in many DRAMs. And we identify those in the profiling stage. in preparation. We also need to figure out what the hammering rows are that are going to be adjacent to the target row that we're going to be attacking, right? So there's some logistics there to be done. We need to figure out address translation and so on. And when the victim enters then afterwards, right, doing signature operations, we inject faults into the signing key that they used. We collect the faulty signatures. Most of the time, this is granted because the signatures are transmitted openly, usually, right? So they're available. And then we do post-processing. Now, the post-processing step is critical. We have only faulty signatures. This is different from differential fault attacks. We don't have the same message being signed with the same key, right? One faulty, one non-faulty. Here we have only the faulty signature, but we have, I mean, it's a signature scheme. We have the public key. We know what a authentic signature looks like, right? We can recognize it if it's given to us. Now, what we do is we take the faulty signature, we correct it. We try to correct it by running through a number of sample faults, right? Or hypotheses. And once we find the correct one, that will reveal to us what the error pattern is. From that, we work our way to the actual data value, the signing key, the bits of the signing key. So here is the main idea really behind that makes it work behind all of this. So assume we are able to flip a bit in an unknown memory location, you know, in a storage of a variable, say S, that holds an integer value, okay? And here's a very simple example, 0, 1, 1, 1, doesn't matter, right? So least significant on the right-hand side, and we flip, as you see, the fifth location, starting from 0, the fourth bit, right? Don't know the location, because that's how Rowhammer works. You don't usually know until, you know, you test it. And if you're somehow able to learn the error pattern, let's say this one somehow, okay, we don't know yet how, but let's assume this is the given error pattern for us, 1, 0, 0. But you see that this is an integer error. It's not a bit error. It's an integer difference that we're getting. If we're able to get that integer differential, then for that location, or we don't even need to know the other locations, right? I mean, what we can deduce from that one bit is, well, if it's a 1 bit, it must have come from a 0 bit, right? So the original bit value was a 0. So although we injected a fault, we are able to deduce the bit value in that location, as long as we are able to get the error pattern. And the same goes for the other direction as well. You go from, let's say, a 1 to a 0 fault, right? It's a Boolean fault, but it manifests itself on an integer value. And because of the negative direction, right, we know that this was a 1 initially, it became a 0 afterwards. So the sign, right, of the error pattern gives us the bit value, and the magnitude gives us the location of where it happened, which power of 2. So that's how we go from error pattern, right, to the actual bit value stored in that location. So this is like a simple thing that we use, a trick to make this work. Now, to flip errors, right, rows, we need to be able to run Rowhammers. There's a lot going on here, right? If you have worked on Rowhammer or read papers, you know that we need to solve a bunch of problems to be able to do so. We need to get around ASLR or KSLR, right? Which is address space layout randomization, physical to virtual translation plus ASLR, and all the way map. I mean, what we have is the code that's going to run. We know the location, right? It's typically dynamic memory, right? So we know, for example, if dilithium's signing key, where it's going to be stored, it's going to be stored in dynamic memory in the heap somewhere, right? And we can get location for static as well as for dynamic by actually probing, by running them, right? The problem then becomes, how can we figure out what the address translation is going to be? Because what we are attacking logically is here, but practically that's what we're attacking, the physical banks. We need to find the hammering locations that are going to be adjacent to that storage. Now, everything here is page-based, right? So we're talking about 4 kilobyte pages that are going to be allocated. And that's why we need that initial online study phase, right? Offline study phase, where we go in and profile tons of pages, find flippy locations, find the adjacent locations, right, that we're going to be hammering so that to create a flip in the target. So I'm assuming Rowhammer is, is known, and we're just going to move past that. So the first attack that we ran, this was published in 2020, was on LUOV, and I see Bart is not here, so happy. Yeah. So it's an MQ. It's a multivariate quadratic signature scheme based on difficulty of solving quadratic multivariate Boolean equations, right? And it's a NIST round 2. It was a round 2 finalist in the post-quantum competition, and this is the first attack we ran. With co-authors Köksal Almuş and Saad Islam. We published it in the ACM-CCS in 2020. So what we're targeting is, again, the signing key, or the representation of it in matrix form that is run inside a signature operation. So I'm skipping a lot, right? The key generation is fairly sophisticated. But what you need to know is, in the end of the day, what we have is a message that is hashed down. And that's what the multivariate equation should evaluate to, given a signature. And to generate that signature, we compute this matrix multiplication, a bunch of operations, hashing, and so on. And this final matrix multiplication, where the important value here is the T matrix. You see the T matrix there. And that's what we're attacking. So we're going to be injecting faults into the T matrix, here a little bit more explicitly shown. And because of the way the scheme is structured, we have what we call oil and vinegar variables, right? LUOV, right? Oil and vinegar. And the oil values are public values, and vinegar values are the secret values. So they are, form the secret key, part of the secret key. And that linear transformation that is used in the signature generation, that is secret, absolutely necessary to keep it secret. Otherwise, you can solve the whole system. Signature is public that we obtain. So ignore the rest of the scheme, the public key verification, any of that for now. Assume we go in and flip one of those entries in the matrix, right? So we go in with Rowhammer, and what's going to happen is the signature is going to come out incorrectly, right? We're injecting a fault, and whichever location we're injecting the fault, the oil value corresponding to that spot is either going to be added. The mic turned off. Ah, okay, now it's back. Or not added when it was supposed to, right? So we are either missing an oil value, or we have an extra oil value added to the signature at that position, right? It's a vector, right? The signature. So now that means what we have, right? What we're able to do is modify the signature, but in a very controlled manner. So what we can do now is we get this faulty signature, right? We flip something, we don't know what we flipped. It's Rowhammer, it's a little bit probabilistic, right? First of all, we check if it's faulty. Yes, it's faulty. It will fail in the verification using the public key, right? But now what we can do is, remember that the oil values are public, right? It's part of the parameter set, right? Or part of the signature. So what we can do is, we can add and subtract the oil values. There's only a linear number of them in terms of the security parameters. And to correct the signature, once we have found the correcting value, right, the sign will tell us the direction just as before, 0 to 1, 1 to 0. And then the row, right, the location will tell us which entry, right, in the matrix was. So we are able to triangulate the value, find out the location and the actual bit value of T. Very simple attack, actually, once you get the gist of it. So here's how we do it in algorithmic form, but that's basically what we do. It's just going through possible error patterns, figure out the error pattern, from that deduce the value of T. And we have attacked the actual NIST submission, right? The reference implementation, the constant time version with AVX. And back then, this was the early version of signature correction. We called it bit tracing for LUOV because we were tracing the fault bit to the output. And now what happens is it takes time, right? Rowhammer is time consuming. You need to hammer and then you get flips once in a while. You see the memory pattern. So this is where the key was stored, rows of T inside a memory buffer, right? And we keep hammering after 1 hour, right? So initially assume it's all black. We don't know any bits. The light positions are the actual ones that we got through experimentation. So after 1 hour, this is how many bits we got. After 3 hours, 2 hours, after 16 hours, we still have some missing bits. And you see there is some banding action, right? I mean, just because of it's a physical device, so there are dependencies. And it takes forever to get, significant portion of the bits. So what we need to do, it's not enough. We're getting bits of the secret key of T, right? Or secret transformation. But to recover the full key, we need to do more. So what we do is, first of all, instead of focusing on the whole thing, we focus on the columns of T. There are some that will be more vulnerable than others just because of the flippy locations, right? And here this shows you the column number of T and the number of bits that we are able to cover, for each different column of T. You see 140 is the best case, right? So that's the best column to attack. And we can use the specific pages to target that we know that are vulnerable in those positions. So what we can do then is, rather than attacking the entire MQ system by injecting the known bits, we target only a column first. And if you target a column, because of the structure, nice, beautiful structure of the signature here, right, the matrix vector, we can reduce the system that's normally a multivariate quadratic system of size 197 by 57. So 197 is the number of variables, and 57 equations are required to identify the fifth column value, right? The fifth column value of T. By injecting 140, the ones that we recovered by attacking column 5, we can reduce this to a 57 by 57 system that you can solve trivially using a SAT solver. Now, the nice thing is that getting the first column to work is tough because you need a lot of samples, but afterwards you get the snowball effect because the values that you recover here, that will also simplify the other systems, the other columns. Yes? Because of the 140. So this comes out in the profiling step. Exactly. In the profiling step, you go after pages, right? We profile the pages. You can either blindly profile and randomly try, right? Which is, the first thing you would probably do, right? And then you say, you know what, if I only, use the pages, right? There's a little bit more going on there. You need to bait the victim actually to fall into those pages, to allocate their signing key into those pages, right? It's sort of backwards. It's like in many of these attacks, there's something called a body allocator. It does memory page allocations in Linux. And you can trick it sort of to make the victim fall into a certain page. By you allocate and then release it, and the last one that was released will be reallocated very likely to the new process. Yeah, we profile often. This takes a long time. Profiling takes a long time, hours. And the one that is most vulnerable is definitely 140, which corresponds with, which is where column 5 of the T matrix would fall into. Okay. So this is the this is how we can get the full, we are able to recover the full. It takes a little over 4 hours to get the whole data to fully break one of the instances here. I don't know which one. Yeah, I think 57, 197, yeah. Okay. And the next thing we attacked was Crystals-Dilithium using the same idea. We said, okay, this works so nicely. There's no reason why, the other post-quantum schemes should not be vulnerable to the same attack. Of course, it's not trivial. You need to figure out the algorithm, how the bit will translate from the point of injection to the signature. The key is that the fault should not grow by leaps and bounds, but should remain isolated to an exhaustible space, right? The error patterns will need to remain exhaustible. Otherwise, this attack won't work. Okay? The fault spreads. And luckily it doesn't, so we're able to attack Crystals-Dilithium, you know, the winner of the competition, right? And right, let's continue. Okay, so if you look at the signing algorithm, now this moved a little bit, the red box, but that's okay. If you look at the signing algorithm, the message is hashed, mu, right? And we have a selection of Y, the nonce. There's quite a bit of stuff going on with sampling, but you can ignore all of those. For practical purposes, we have C, that is the hashed version of mu, plus W1, right? That's to fix the key. And then you have a sampling operation. Now, after all of this, you have the challenge C, right? Times the secret key S1, added with the nonce Y, giving you the signatures in step. And the critical point there is, you know, wherever the key is used, that's a potential target, right, for our attack. So if you can flip bits, right, in S1, and if they will able to go through rejection sampling later on, we'll be able to get faulty signatures out of this. And maybe we can run the same thing. And, you know, and this work, by the way, was again published with Islam, Mush, Singh, Patrick was part of it, Shamont, and myself, published in EuroSMP this year, earlier this year. So let's look closely. So Z would be the original signature, Y plus C times S1, S1 being the Z is public, Y is secret, and S1 is secret, right? And if we inject the fault in S1, we don't know where we injected the fault again. You know, it's polynomial. It's 4 polynomials actually in dilithium. And we have a faulty signature coming out, Z bar. Now, because of the structure of the dilithium signatures and the polynomial represented, if you flip a bit, right, it's going to flip a bit of a coefficient in the S1 polynomial, one of the S1 polynomials. There are 4 of them. Each one has degree at most 256. So we're flipping a coefficient. The coefficients come from a small space, but they are, again, integer-based. That's critical. And we're flipping a bit of it, which means the same idea would work. We can quantify the differential like this, and by running, again, corrective steps, right, we can identify the error pattern, just like before. So to do that, we have actually run, you know, experiments again, you know, the same thing, profiling of the memory, identifying flippy locations, figuring out where S1 would fall in the reference implementation in memory. And then actually, you know, the storage is organized into 4 buffers, each one holding a polynomial. And each polynomial has 256 coefficients. So each coefficient is represented in a row here. And each coefficient is represented in 32 bits. It's a, and coefficients come from -2, -1, 0, +1 to +2. So that kind of range. It's a tiny range represented in 32 bits, okay? And that has to do with the processing, because you're doing these operations to prevent overflow. They over-design the storage for it. And when we, you know, do the signature correction attack, we're able to get these, flips in these locations. You see black bands, those are the bits that we're not able to get. They're either not flippable locations, or they are eliminated because of signature rejection. There's rejection sampling. And this kind of makes sense because you see the stripe here is around the region where the signature rejection would apply. And the green ones are, if I remember correctly, zeros, and the red ones are 1 bits that we recovered. Okay. If you take a closer look, the meaningful portion of these coefficients that we recover are the first few bits, because it's a -2 +2 range represented in 2's complements. Most of the bits, you know, after the 3rd bit, all of the bits are just the sign bits repeated over and over again. So if you get any bit from any location beyond the first 3 bits, it's just the last bit. So all the information that we want is really in the first 2, 3 bits, right? The 3rd bit is just repeated all the way through. And so we're good to go. I mean, we can, with whatever we get beyond bit 3, we can map that back to the sign bit. And if you're getting bits from the first 2 locations, that's awesome. We're getting the full coefficient then. Now, the goal then is to figure out, you know, what this does to the lithium, right? I mean, it's not as obvious as getting a bit from a team. It's a little bit more complicated now, right? We're getting lots of partial information. We can use the encoding to our advantage, right, with the sign bit. And there are also possible patterns because of two's complement. And by processing these bits a little bit more, we're able to recover 129 additional coefficients. And we get 200 additional recovered bits by processing it. There are cases that cannot occur because of the two's complement representation. And now what that does is, you know, in terms of the attack, so this is the decoding shown a little bit more in detail, right? So lots of tenuous bit manipulation. Yeah, so we have fully recovered coefficients, and then we have bits recovered, right, from the coefficients, a few bits here and there, right? And there are a lot of them. Now, the fully recovered coefficients, what they're going to do is they're going to help us reduce the dimension of the lattice attack we're going to be doing, right? So the difficulty in solving or of this challenge is quantified by the lattice system, right? The dimension is as part of it, the norm, and so on. By recovering each coefficient gives us a lot. It reduces the dimension by 1. And then the additional bits that we recover, they can be used to reduce the norm of the coefficient. So the norm, the original norm, is square root 10. You can reduce that a little bit, right? With the coefficient. So, and with the fully recovered coefficients, we have 228 of them. The remaining coefficients are 796. So it's still a pretty big system. Normally it's 1024 dimensional. We're getting about maybe a quarter of it, right? Now, what does that do? So if you put these together, so this is what we end up with. We have reduced the security of dilithium down to, so first of all, there are 2 ways of attacking the scheme. So this is based on the original analysis proposed by the authors of dilithium. We just followed in their footsteps, right? We even used the software that they used, right? It was originally proposed for New Hope, right? Figure out the dimension. So there are 2 types of attacks, the primal attack and the dual attack. And we care about classical and quantum based on these 2 parameters, M and B, that are chosen. M is the sample size, B is the block size. And the value eta here is the target norm, which we're able to reduce with the partial coefficients to the one we have in the bottom. And we're able to go all the way, you see, with 0 coefficients recovered, right, and full norm, that's the original level. Both quantum and classical, they're pretty high. Quantum is 128, and classical is 141 bits, right? And then if we introduce the partially recovered bits, you see the norm shrinking. Assume the dimension is the same, so no recovered coefficients. Goes down a little bit, right? But not much. And once you insert, also take out the coefficients, right? You can do it progressively just to see the change. We end up all the way down here with 80 bits, 81 bits of security. So this is breakable now, right? Yep. You don't believe me? Okay, good. All right, just checking. So 81 bits. So 80 bits is roughly where we get a Bitcoin, right? To be mined. And with a little bit of resource, you can do that. And this is not the end of the story. You can do better now. We have faster Rowhammer. We have more effective Rowhammer attacks, right? As well as this is highly dependent on the DRAM that you're attacking. We have done this work initially on DRAM 3 and then with DDR3 and then DDR4. We have another setup that we ran after this attack. It's more flippy. We get more bits out of it. It's not included in this. So again, I mean, another example of signature correction. All right. So With Rowhammer, we have done quite a bit, right, on LUOV and dilithium, right, with signature correction. I said, but how about other fault models, right? In the end of the day, this is about injecting faults. If you have full control, if you know the locations, that's a different ballgame. You can do better than signature correction. But if, as far as these software-only faults are concerned, right, that we're going after, another type is called, that came out a couple of years ago, is Plunderwald. I don't know if you heard about it. Has to do with the fact that you can undervolt a system through software, right? And this was allowed until this attack came out later on. There was a firmware patch and Intel disabled this. Unless you're root, you cannot do this anymore, right? So there was a patch came out. And the root cause is still there though. So in some certain settings, this might still be warranted, this attack. But we got curious. So what happens, right? So if you undervolt, what's gonna happen is, and maybe Ingrid knows this much better than I do, right? The logic cells will flip, but maybe not all the way to completion. And we will have instructions that are somewhat halfway completed, especially the ones with high critical path delay, right? That are close to the clock edge. And we wanted to compare this to Rowhammer, see what we're getting out of it, right? So can we use this to target post-quantum schemes and then also DVFS, right? Voltage and frequency scaling, which I'm not going to go into, but that's another open area for research. So with Plunderwald, we ran a bunch of experiments, and indeed we're seeing faults when you run dilithium. And we have noticed most of these faults are in the multiplication operations, not surprisingly, right? Obviously, you're multiplying, it probably has more of a critical path delay, right? And because of the way the faults are injected, we cannot really run the signature correction attack here anymore with Plunderwald. We're getting faults, but this is maybe more suitable for something like, you know, if it's a determined. The problem is the fault that is injected, it spreads, right? It doesn't remain limited to an exhaustible space anymore. So it does more than that. Okay. And, but in any case, we're seeing faulty signatures coming out, right? The more you undervolt, obviously, the more faults you will see. And one side effect is if you push it too hard, you also get system crashes. And that said, I also should note that if you're doing Rowhammer in a careless manner, right? Like the one that we did, where we were careful about, you know, attacking certain pages, specific place. If you randomly try to flip everything with, you know, very aggressively, there's a good chance you will crash your system. You will, you know, flip something where you're not supposed to, because, you know, it's page allocation, dynamic, and so on. It moves lots of pages in and out, including kernel pages. Okay. And finally, just one slide about the effectiveness of the countermeasure. So what can you do to prevent this kind of an attack? There are obviously any countermeasure against Rowhammer should work, right? Reducing the refresh rate or increasing the refresh rate, reducing the time will make a massive difference to get rid of it. It doesn't completely eliminate it. I remember there was a paper at USENIX, right, where they showed you can, if you increase the target refresh rate for the adjacent rows where you're hammering, right? I think the Graz team had another attack where you can, you know, from 2 edges, like with a stride of 2, you can still get the same kind of effect. It's smaller probably, but still works on non-refreshed rows, right? By targeting non-refreshed rows. You can do randomization and some other techniques that were proposed against, like, for example, to prevent DFAs. They don't apply here. You can use some kind of redundancy to store S1, for example. The kind of stuff we used to do in chess in the early days in embedded systems. You know, you can use temporal, you know, time-wise redundancy, move things around, introduce delays. None of them are, you know, foolproof. I think the best solution still is just to verify after sign. At least it's the easiest to implement. It takes care of a lot of the attack vectors. And even that by itself is not foolproof, because that can also be a target of an attack, of a fault injection attack, obviously. And that concludes my talk. All right, thank you.